The first scalable implicit solver for
It's very
nonlinear
good.
wave
Thank you.
or
Yeah.
low-order unstructured finite element to enhance comprehensive earthquake simulation. We are aiming to realize comprehensive earthquake simulation from fault to cities. Huge computational cost is a bottleneck to the analysis of more complex and higher physical components. Great leap is needed, so we are trying to reduce this huge computational cost with computational science research. Here's the results of earthquake simulation with supercomputing. These are published at the Supercomputing Conference 14 and 15. So the major computation cost is from the soil amplification process, the nonlinear wave propagation. So we have the high fidelity soil structure data set. So if we can use this, dramatically improve the reliability of earthquake disaster estimate. But this simulation raised huge computation cost. So this is the key for the simulation. So here is the numerical modeling of nonlinear wave propagation. The target is a complex domain with local complex geometry. So that's why we want to use the unstructured low-order finite element. Because we want to model the geometry correctly. The finite element model, low-order unstructured finite element. Its element size is less than 1 meter. So this led the huge degree of freedom. Here the discretized equation for the nonlinear wave propagation. This is a standard finite element, but its dimension, the huge. So that's why we have to care how to solve this kind of huge problem. So now it's time for supercomputing. We want to speed up massive implicit unstructured low-order nonlinear finite element solver. The viewpoints for the design of solver on supercomputer are random access dominant kernels, the scalability, the up to more than the 1 million parallel computation, the fast, good time to solution, and efficient use of memory. The limitation of the memory amount due to the huge degree of freedom. Here's our proposed solver. Here we summarize the key point. We use a conjugate gradient method. One of the special tuned conjugate gradient method that's based on adaptive conjugate gradient method. In the adaptive conjugate gradient method, we can use the special tuned preconditioner. Here we use that we combine the multigrid and the low precision computation. Here. So use a multigrid method to reduce the compute cost of the preconditioner. Use a single precision in preconditioner to reduce computation and communication. With the extensive use of the solution space and precision space, so we can reduce the computation cost. Here's the performance of our proposed solver. We got a high efficiency on the K-computer, Fuga Computer Summit, and PZN and OFP. Here you can see the weak scalability. It's almost flat. And we can treat by this solver up to 1 trillion degree freedom. Here's one of the application examples. So here's a not so large scale problem. They're small, but its degree of freedom is not so small. Its element size is 0.66 meter. Here we use a second order tetrahedral element. We construct a 3D finite element model. And we decompose it for the parallel computation. And using this 3D finite element model, we conduct the nonlinear wave propagation in the software. This is the response of the 3D solid structures. So using this ground motion, we simulate the response of the buildings here. Then we can compute the response of the city, the regional scale, but this is not so large. Yeah, we see the complicated response of the cities. So why we need this kind of the huge degree of freedom simulation? Now because we need high quality computing. First, I'll show you the numerical convergence of the solution. We use the 10 billion element model for this simulation, and we conduct the 0.4 element model and 3 billion element model. Here is the distribution of A star and surface. And the difference between 10 billion element related 0.4 billion element, 10 billion minus 3 billion element. So that we can see its response is converged. So next, I'll show you the waveform. Compare waveform at this point. So here's the response from the 10 billion element model. And here you see the difference between the 10 billion element model and 3 billion element model, 10 billion element minus 0.4 billion element model. So you see we can get the combined solution. So we have to ensure the quality of the numerical simulation. So that's why we have to use this kind of huge degree freedom program. So next is how to consider the uncertainty of the city. So the actual city have large uncertainty. So here is 12% difference in the stiffness. Its response is very different. So using this, the stochastic distribution, we generate a lot of the structures, and we conduct the response simulation. This is Monte Carlo simulation. So now our target is the city. So we do the stochastic simulation of the city by the Monte Carlo simulation. So here we do the Monte Carlo simulation. First 100 samples. So here you see the stochastic response, the structure A and structure B. So 100 samples, 1,000 and 10,000 samples. So you say the stochastic response is compiled. So this is how to consider the uncertainty of the city information. So the large-scale simulation can treat this kind of the stochastic problem, and high-performance computing it has some contribution for the ensure the quality of the numerical simulation. So next is the high fidelity fault to city to social simulation using a full power of the K computer, targeted Tokyo metropolis. So first we conduct the earthquake ground motion simulation from fault to the surface. This is a linear wave propagation. So this is up to the target frequency 10 Hz. the 56 billion degree of freedom model. So this is almost the state-of-art level, but its computation cost is not so large. So next is that we do the city simulation with the nonlinear wave propagation simulation. So this is the target area. So the soil structure and the buildings. The 10, almost 10 kilometer and 10 kilometer. This is a 3D finite element model. Its distribution is huge. So this is a 3D finite element model. This is automatically generated. So its detail. We use a second order tetrahedral element. We decompose it for the parallel computation. The one computer node computer 1.6 million degree freedom problem. We synchronize all the small domain, decompose the domain. We compute the soil structure response, the nonlinear propagation in soft soil. This is the complicated, the strong ground motion generated by the complicated soil structure. So using this strong ground motion, we compute the response of the city. Here you see there are a lot of structures. So we simulate the response of each building one by one. So there you see its response of the city. It's very complicated. So this is the strain distribution inside the soil structure. Now, of course, it's difficult to observe the strain distribution inside soil structures, but via this kind of a numerical simulation, we can see the strain distribution. Now, this is useful for the lifeline or so. So finally, we can compute the evacuation process in the city. My colleague, Professor Lares, conducted this agent simulation. Here, there are 2 million evacuees in this 3D city model. All the behavior is simulated by the multi-agent simulation. So this is the result. So we conduct a high fidelity photo city to social simulation. All phase of the earthquake simulation at the state-of-art level. So we need a more computational capability. So that's why we need a new supercomputing method with data learning. This is published in the supercomputing conference. So I think. So the new fast scalable implicit solver with data learning. Use information of underlying governing equation. The governing equation's characteristic with discretization condition should include information about the difficulty of the convergence in implicit solver. So extract part with bad convergence via data learning and extensively solve extracted part. So that improve the time to solution. Here's the schematic view of the new proposal solver. Here, the artificial intelligence or data learning extract the a part of the target domain. This is the code of the but convergence in the implicit solver. So here you can see the SC14 is the state of a solver, and this green is our new proposed solver. This is the weak scaling on Summit. You see it's weak scaling almost flat to the full system of the Summit. So that means we can get a good the score on the Summit and the GPU supercomputer. And this is the result of the urban earthquake simulation with data running on Summit. So this is a full couple simulation, the soil structure and buildings, underground structures. The complicated the response, the underground structure and building, all the behavior is computed with this 3D finite element model. So using the solver, there is a lot of applications. So here the cluster deformation analysis in Cascadia subduction zone. So on Summit, we achieved 400 petaflops fast scalable implicit solver. So it kernel level the exascale flops is achieved. So the target domain size is this is huge, and its degree of freedom, and only the almost 20 seconds that with compute node Summit is used for the compute the response of the cluster deformation. And this is a seismic structure response with high fidelity model. So they see the all the structure is modeled with second order tetrahedral element. Its minimum size, the 16 millisize element. So it's huge, but we can compute it. So with this advancement of the computational method, so we can conduct this kind of complicated state simulation. This is the full couple analysis, so the soil structure and buildings underground structures. So here's a summary. We developed the first implicit matrix solver and realized large-scale, high-fidelity urban earthquake simulation. So that's all.